Okay, so last time we proved the following theorem. So the maximum minimum principle for Laplace equation neydi bu? U x y is a function which is twice continuously differentiable on some domain and continuous on the closure of that domain. So suppose this is a solution. So let be a solution of the Laplace equation, which is just u sub xx plus u sub yy equals 0. Where this is a bounded region. Since this is bounded, its closure is bounded. Therefore, closure is closed and bounded. Therefore, it's a compact set. And therefore, U has a maximum and minimum on that compact set. The conclusion is that then the maximum and minimum values of U on omega is the same as maximum of U on the boundary of omega, and the same thing for minimum of U x y So last time we proved this. Actually, we proved the first statement, maximum one. What about the minimum one? Well, you see, I mean, if U is a solution of this, minus U is also a solution, right? And the minimum value of U is the maximum value of U bar. Therefore, you just apply the theorem what we have proved for U to U bar, and then we see that maximum of U bar occurs at the boundary, but maximum of maximum of minus U is just minimum of U. Therefore, minimum of U also occurs at the boundary point. Değil mi? Yani U bir çözümse eksi U da bir çözüm ve birinin maksimum, diğerinin minimumu. Dolayısıyla sadece maksimumu ispat etmek yeterli. Anlaşıldı mı burası? Pek inanmıyor gibi bakıyorsunuz ama. Okay. We proved only the maximum part, but the minimum part follows from the maximum part. Why is that? Because if U is a solution of the Laplace equation, then minus U is also a solution of the Laplace equation. And minimum value of U is the maximum value of minus U. And we proved that maximum occurs on the boundary. Therefore, minimum value of U, which is the maximum of minus U, will also occur at the boundary. Okay? Peki, bu teoremi ispat ediyor. Ondan sonra bir de şu var. Bunu da yazayım. Teorem the maximum minimum principle for Poisson equation. Okay. So let omega be a bounded region with boundary omega. Let U be a solution of the Poisson equation. What is Poisson's equation? Which is this one. Del squared U xy, which is U sub xx plus U sub yy is equal to F sub xy. So non-homogeneous Laplace equation. That's called Poisson equation. Okay. All right. Then the conclusion is this. İki tane statement var. If fxy is positive in u, not u, in omega, then the maximum of u is attained on the boundary of omega. Eğer negatifse if fxy is negative, then the minimum of u occurs on the boundary. Again, as in the previous theorem, it is enough to prove only one statement, because, you know, if we prove this, namely, if f is positive inside this region, then u attains its maximum on the boundary. Then if I multiply everything by -1, minus u will be equal to minus f, but that time f will be negative. So you will obtain this statement. Therefore, it is enough to prove only one of them. Okay, so proof. Note that it is enough to prove only one of the statements. Say I. Yani sadece i'yi ispat edelim. Ne demek bu? Yani okey. Yine u is a continuous function and closure of omega is a compact set. Since u is continuous, Onu söyledik mi? Yani kim söylemedim ama yani öyle kabul edin. U yine işte ilk teoremdeki gibi continuous vesaire olsun. Since U is continuous on the compact set it has a maximum in this region. Assume that the maximum is assumed is reached at a point x0, y0 in omega. Biz ne diyeceğiz? Hani boundary'de de aynı değere ulaşacak şey. Değil mi? Onu göstermemiz lazım. Peki. Okay. Şimdi içerideki bir noktada maksimumu olduğuna göre as in the proof of the previous theorem by the second derivative test at this point u sub xx should be non-negative and u sub yy should be non-negative. Why is that? Because otherwise, if one of them is positive, suppose this is positive, then, so your region is like this, and you are at this point, x0, y0, and the second derivative along this line. So when you restrict your function to this line, it's a one variable function of x, and second derivative is positive. Then you should have a minimum at this point, right? Yok. Second derivative pozitif ise minimum var. Tamam. Ama biz hani maksimum olduğunu söylüyoruz, değil mi? Yani fonksiyon strictly increasing. So it is strictly increasing on this line segment. Therefore, when you pass this point, and you can pass this point because this is an interior point, it is not on the boundary. Therefore, at this point, the function cannot have a maximum value, because if you go a little bit further, it will take bigger values. Okay, that's why both of them should be non-positive. Okay, then what? Bunları yerine koyarsak, but then u sub x x0 y0 plus u sub y x0 y0, which is f x0 y0, because it's a solution of this equation, Poisson equation. Therefore, this function is negative, non-positive, but this is a contradiction, which is a contradiction. to the assumption. Right? We assume that f is positive inside this region. Therefore, the proof finishes. This finishes the proof. Ha, niye bitiyor? Yani x0, y0 noktasında o zaman maksimum olamaz. Yani şöyle yazayım. So this means what? This means that the point where it reaches its maximum cannot be inside the region. Hence, x0, y0 is not in this region, so that it is in omega bar, but not in omega, therefore it's on the boundary. Okay, so this finishes the proof. Kaldı, evet. Özür dilerim. Ama donuk çalışıyor. Anlaşıldı değil mi? Okay. Şimdi bunların sonuçlarını görelim. Let omega be as in the previous theorem. So it's a bounded region, and its boundaries omega, boundary omega. Then the solution of the Dirichlet problem So problem is this: we have an equation inside the region, and on the boundary u is equal to g. Then this is unique. Then the solution of the Dirichlet problem is unique if it exists. Yani varsa unique. Yoksa bilmiyoruz. Efendim? Bilmiyorum. Dirichlet problemi yok. Dirichlet problemi neydi? F'e eşitti değil mi? Yani herhalde evet, normalde yani biraz daha genel bir problem. Aslında Dirichlet problemi olarak f yerine 0 yazılmış. Buraya bir şey verilmiş ama bu daha genel. Muhtemelen o şeyle ilgilidir. Hani f bir force fonksiyonudur. O pozitiftir ama denklemde onun negatifi geliyordur. Hani physical bir nedenden dolayı böyledir. Var, oradan yapıyorum zaten. Da hani ispat aslında hani kalkülüsten öteye gitmiyor. Değil mi? Zaten matematik genelde öyle. Kalkülüs artı linear algebra. Biraz da cebir var. Okay, so let u1xy and u2xy be two solutions of the problem. Yani ne demek bu? So grade del squared u1 is minus f, and that is equal to this. And so in the region omega, and u1 is equal to u1 xy is equal to gxy, and this is u2 xy on the boundary. Okay. Well, let v to be u1 minus u2. Then, of course, del squared v, which is just, right, if you take Laplace of this v, it is just Laplace of u1 minus Laplace of u2. So this is Laplace of u1 minus Laplace of u2. Both of them are equal to minus f, therefore this is 0, right? Minus f minus minus f, so it is 0. And of course, v of xy on the boundary is equal to gxy minus gxy, because u1 and u2 both is equal to g on the boundary. So we have this. So this v is a harmonic function. Its Laplace is 0, and it is 0 on the boundary. So that is the first problem, right? Not first theorem. Şimdi first theorem ne diyor? So by the first theorem, V has maximum and minimum on the boundary. Both the maximum and minimum values of Vxy must occur on the boundary, right? It is the statement of this theorem here. Right? If we have a solution of the Laplace equation, the maximum value, bunu yanlış yazmışım. Şöyle yazmak lazım. Değil mi? Yani çünkü içeride maksimum olmayabilir bile. I'm sorry. So it should be like this. So maximum and minimum should occur on the boundary. But in our case, our function is 0 on the boundary, right? It is constant 0. Therefore, the maximum and minimum values of of v are both 0 on the whole region, right? On omega, therefore, on the whole region. If a function has both maximum and minimum equal to a constant, then that function should be constant, and it should be constant 0. So, right, V is just 0 on the boundary, hence Vxy, since both minimum and maximum are equal to 0, this function should be constant and equal to 0 on the whole region. Değil mi? Çünkü bu fonksiyonun bütün omega bar üzerindeki maksimumu da minimumu da 0. Dolayısıyla bu fonksiyon constant. Anlaştık mı? Ama bu da ne demek? Thus V is 0, therefore U1 minus U2 is 0 on omega bar, but this implies U1 is equal to U2 on omega bar. So the two solutions are the same. So this is the uniqueness theorem for Dirichlet problem. Bir tane daha teorem var. Kaldırayım. Bu kalsın, şu teorem. Belki bunu kullanırız. Şurayı sileyim. Okay. So the last theorem is this. The solution of the Dirichlet problem depends continuously on the boundary data. Bu arada şey söyleyeyim. Why the uniqueness is important for you know, that problem. So we have this. This is equal to some f, and u is equal to some g on the boundary, right? This is probably the flow of some liquid or some, maybe, I don't know, electric charge or, you know, something like that. It has a physical meaning. And if this problem has more than one solution, then it means that, you know, the liquid under the same conditions might behave in different ways. And this is not, you know, good, right? I mean, if the conditions are the same, external forces, etc., and the boundary conditions, then you expect to, you know, you expect to have the same kind of flow. Otherwise, it means you cannot just control it. Değil mi? Yani yani o zaman mühendislik olmaz. Hani ya da hani bu şey demek, yani siz bunu anlamamışsınız demek, değil mi? Bu flow'u etkileyen başka şeyler var ve bu denklem onu açıklamıyor demek. Okay. Okay, now let U1 and U2 be two solutions of del squared UI equals F in omega and UI equals Fi on the boundary. So we have two different problems, okay? Two different Dirichlet problems over the same region, omega, okay? So you have the same region, omega. Here, del squared U1 is equal to F, but U is equal to F1 here. Here, we have the same differential equation. Del squared U2 is equal to F, but on the boundary, F is equal to F2. And we are trying to understand how the two solutions, U1 and U2, differs when we change the boundary data. The equation is the same, but the boundary data is different, and we want to understand how the solution depends on this boundary data. And the theorem tells us that it depends continuously on the boundary data. This means what? This means that if I change F a little bit, then the solution should change a little bit, right? That's continuous dependence. Yani hafiften değiştirince patlamayacak. Değil mi? Eğer continuous değilse o ne demek? Çok az bile değiştirseniz bir anda bir şey sonsuza çıkabilir demek. Fiziksel bir şey sonsuza çıktı demek, o patladı demektir. Değil mi? Yani bir kuvvet sonsuza çıkıyorsa yakınında olmak istemezsiniz. Okay. Peki, şimdi görelim bakalım ne olacak. Bu tabii göremedik. Kameranın şeyi biraz zayıf. Algısı. Okay, let V is U1 minus U2. Then, as before, what is this? Well, this is just U1, U2, right? So this is F minus F, which is equal to 0. Therefore, also V is equal to U1 minus U2, and that is just F1 minus F2 on the boundary. Okay. Now, by the maximum principle, the second version, we have a solution of the Laplace equation. It doesn't have to be actually homogeneous, and we have some boundary condition. Then what was the condition? The maximum of this should occur. Pardon. Burayı sıfır alırsak yine birinci teoremi kullanacağız. This is zero, therefore the maximum and minimum of V should occur on the boundary. So again, by the maximum minimum principle, the maximum and minimum of Vxy on the closure of omega should occur on the boundary. Right? O halde bu ne demek? Bu fonksiyonun maksimumu da minimumu da bunun mutlak değerinin maksimumunu alayım. The maximum of absolute value is either the maximum value or its minimum value, right? Bir fonksiyonun, değil mi? Mutlak değerinin maksimumu nedir? O fonksiyonun minimumuyla maksimumunun mutlak değeridir. Right? So the maximum of this is either the maximum of V or minus the minimum of V. Yani plus or minus. Değil mi? İlla ki öyle olmak zorunda, değil mi? Maksimum, evet. Ama biz ne biliyoruz? Maximum of V or minimum of V should occur on the boundary. Therefore, this is just the maximum of this function on the boundary. But on the boundary, this function is equal to f1 minus f2. So therefore, this is just the maximum of f1 minus f2 on the boundary. So the maximum of the difference of u1 and u2, right? This is just equal to maximum of u1 minus u2 on the whole region is this maximum value is equal to this gadget. Yani bu eşit, evet şöyle diyeyim, maximum of this f1 minus f2. Therefore, I can say this, u1 xy minus u2 xy for any xy in the region, this is less than whatever that maximum value is, okay? So it is maximum of the difference of these two functions. Dolayısıyla da we see that the difference between two solutions cannot exceed the difference of f's f1 and f2. Therefore, this solution depends continuously on the initial on the boundary data. Değil mi? Yani boundary data ne kadar birbirinden yani farklıysa, hani iki tane değeri, çözümlerde en fazla o kadar fark ediyor. Dolayısıyla bunların farkı hani çözümlerin farkını domine ediyor. Tamam mı? Peki. Dört, beş, altı. Tamam. Şimdi evet. Devam edeyim. Şurayı silelim. Ben kayıt yapıyor muyum? Ne yapıyormuşum? Okey. Uh, Green's identity and solutions. Biraz daha kalkülüs yapacağız. Okey. Bunu çak mıydım? Hı. Evet. Ee, Şöyle bir şey var. Ee, Neredeydi? Özür dilerim. Let omega be a bounded region again. R2 and with smooth boundary omega, del omega. So boundary is smooth means it has no corners. Okay. So something like this. Okay. Yani şu, I don't have something like this. Okay. With corners. Then okay. Then for any differentiable function, f x y on okay. We have. Şimdi tabii closure'ın da differentiable deyince belki şöyle düşünmek lazım. Hani f bu region'ın şöyle hafiften bir komşuluğunda da tanımlı ve differentiable. Çünkü öbür türlü hani şurada türevlenebilir demek çok anlamlı değil. So we may just assume that f is differentiable on an open set, small open set containing this region. Then we have the following. We have this is Green's theorem. Gradient of f n dot ds. So n is what? N is just the normal vector, outward normal vector, like this, and ds is the arc length element. Arc length element. Now, what is NDS? It is, you may just think it this way. So this is the tangent vector is just dx dy. I can regard it as dx dy. Niye? Şöyle düşünün. Şöyle yazayım. Suppose I have a parameterization r t, which is xt, yt. Then what is the tangent vector? So rt is just a parameterization of the curve. Then r prime t is just x prime t dt. Ya da şöyle diyeyim. dr dediğimiz şey değil mi? Differential'ı x prime t y prime t dt. And we call this dx and this one dy. It is the tangent vector here. What about this normal vector? And it is perpendicular to this one. And if you just think about a minute, this is just minus, no, it is dy minus dx. Niye böyle seçtim? You see here, dx is negative and dy is negative. But here, the x direction, no, y direction should be positive because it's going upward. Therefore, I should have minus sign here. Not here, but here. Değil mi? Yani birbirine dik iki tane vektör seçeceksiniz. This should be perpendicular to each other. Well, it is. But it's not clear whether I should take this one or this one. We choose this one because of what? Here, both of them are negative. It is going in this direction. But here, x direction is negative, y direction is positive. Therefore, I should have dy here and minus dx here. Tamam mı? So, my n is just, so here I have boundary omega. What is nabla x? It is just gradient f sub x and f sub y. And here I have n ds. N ds is just dy dx. So dy minus dx. So this is just f sub x dy minus f sub y dx. And by Green's theorem, Green's değil mi o? Green's theorem, this is just equal to integral inside the region of what? Green theorem neydi? Green's theorem was this. If I have, let's say, m dx plus n dy, right? This is equal to integral, double integral over omega of nx minus my. Öyle miydi? Nx minus my dA. Area integral. Bununla karşılaştırırsak o zaman ne olacak? M is minus f, n is f of x. So x derivative of this, f sub xx minus y derivative of this gadget, f sub y, but it has a minus sign also, another minus sign, so it is just plus f sub y, and then I have dA here. Okay, so this means what? The line integral of gradient of f over the boundary of this region with respect to this, okay, is equal to just the integral of the Laplacian of f inside the region, okay? All right, so yes, let me stop here.